These are the notes for exponential growth. This is kind of part of section 6.2 in your book. It'll be the second to the last thing we cover as far as material for the AP test. So let me explain what's happening here first. And to avoid some memorizing, I am going to derive, this is a formulaic section, but I'm going to derive it first. So just in case your memory fails you, you will always be able to create this as you go. So what we've got here is the rate of change of some quantity, and a rate of change we've said is a derivative or a differential. It's the change in y, and we're going to be doing these with word problems. So basically we're always going to be doing some change in a quantity over time. The y will vary depending on what's changing. It might be bacteria growing over time, or money growing over time, or air leaking out over time, but there's some quantity that over time it's changing. And when we say it's directly proportional to y, you should have learned in Algebra 2 that when something's directly proportional to a quantity, it's a constant multiple of it. So then they give you some examples of exponential growth, and you can read through those if you want. But what I would like to do is have you go down right here. So what we have is some quantity y that's changing over time, and it's directly proportional to that quantity. And so we can set up this equation whenever it says directly proportional. Now the same thing happens every time you do one of these. The only thing that's going to kind of vary in here as far as when we go through it the long way here is your value of k. But what happens in the end, we're going to do it by hand here first, then we'll come up with the formula. So let's go ahead and write this down. We've got a rate of change over time that's directly proportional to that quantity. Okay? And so what I need to do here is separate my variables. So I've got it set up, and so let's separate. We're going to divide by y. We get dy divided by y, and I like to write that as 1 over y, just so you can see the function of y is 1 over y. And that would be equal to k dt. Move that over. So what we've always done with our differential equations, we're going to separate them first. We're going to integrate them next. So I will have the integral of 1 over y dy equal to the integral of some constant dt. And we've said that the integral of 1 over y is the natural log, technically of the absolute value of y, so I'm going to keep that in there, and plus a constant, is equal to the integral of a constant with respect to time, which will just be kt. Again, when you take the derivative of kt, you get just k, so it is its antiderivative. And then we combine both constants on the right-hand side. So I've just performed my integration. Now next, again, our goal is to solve for y. We want to come up with an equation that will help us get that quantity and how it's changing over time. So usually the end result of this, your goal is to predict the future, really. You're going to give me an equation for the quantity that's going to be dependent upon time. So in order for me to get in here and get at that y, I've got to do the inverse operation. So I'm going to raise both sides. E will be the base on both sides. So I've just written this exponentially. The absolute value can be dropped. I really don't like this explanation of why it can be dropped, so I'll give you another one in just a minute here. So again, these are inverse functions. E to the ln of a quantity is that quantity. And on the right-hand side, I still end up with e to the kt plus c. All right? So now what I'm going to do is split the right side into two factors. So I've got y is equal to e to the kt, and we did this extensively in our last unit, so I'm really not doing any new math here. I'm just going to be applying it to some growth models. So remember, we have been calling this some constant, and this is where I like the explanation for getting rid of the absolute value. If we can define that new constant as e plus or minus e to the c, then we're able to drop the absolute value, and I think it makes more sense why it can drop then. So we just have some other constant here that's a plus or minus, allowing us to take the absolute value off on the left-hand side. So I'm going to write that as constant e to the kt, because e to the c, again, is itself. It's just simply a constant. Now, this always happens. Okay? It's very formulaic. Whenever you can set up that change in time is directly proportional to the quantity itself, when I work it all out, I will always get this model. And even furthermore, if I say, well, what happens at time 0? Well, at time 0, I'd have c times e to the 0, which is just c itself. So what happens is, when t is equal to 0, I get that constant. So sometimes what we'll do is we'll say, well, this constant's always going to be what happens at time 0. So they'll write it as y sub 0, e to the kt. And again, once we apply this to an actual problem, we'll get a better visual of what's going on here with all the y's and the k's and the t's. But for now, let's go to the next page here. So this is what I just worked out for you, and I think it's important. It says know this backward and forward. I would say if you can create it, you don't have to memorize it, but let's go write it down. We've got a quantity changing over time that's directly proportional to that quantity. Every time we have that situation, we can conclude that the quantity is going to be equal to some constant times e to the kt. But this constant is always going to be the starting amount. So we write it like this. Notice it looks very similar to the formula you had for continuously compounding interest, and I don't know if that was Algebra 2 or Pre-Calc, but we call it PE to the RT. And remember, this is the amount that you start with at time 0. It's your principal amount. And then we have our interest rate that needs to be given or found, and we can predict what happens or how much our money grows over a certain amount of time. So you've really dealt with this model before. You just dealt with it in a very specific situation, and now we're going to apply it more generally to anything that's got a rate of change that's directly proportional. So let's go do one. So we run over a nail, and as the air leaks out of your tire, the rate of change, that's a key to your derivative, of the air pressure. So I like to use the variable P for pressure or B for bacteria. I would like to say that the change in pressure over time, and then it says is directly proportional to that pressure. All right, this is called my differential equation. Now, again, what I've told you is the only thing you really need to worry about is the C, which we're going to worry about later in the problem, and the K. So let's see what we've got going here. In this model, they say that if the pressure is 35 pounds per square inch, that's the P, and it's decreasing at a rate, well, decreasing means going down, and our rate of change is our derivative. So really what they're telling me here is that it's negative 0.28 is equal to K times 35. And I can solve this for K by simply dividing. And if you do that, you'll get K is about 0.008, and it's negative. You can do that on your calculator. But this is what they mean when it says set up a differential equation. Now, when it says to solve that differential equation, if you've got the model memorized, you can simply just go use it. You can simply say this, well, my pressure is going to be equal to the pressure that I started with times E to the KT. Well, what pressure did I start at? All right, so that's kind of what you need to figure out here is what was the starting pressure. Well, they told me that, I think they told me it was 35, and I just solved for my E, my K, sorry, 0.008 T. So this is my differential equation solved. Now again, had I gone through the whole thing, like started with this, separated my variables, integrated, etc., it would have led me right down to this model. So you can always create it if you need to. Now when it asks what the pressure is after 10 minutes, I simply can use my model to predict the future. So I'd say my pressure is equal to 35, E to the negative 0.008 times 10. And again, if you go to your calculator, I'm just going to give you the answers to these to save time and calculation. You get about 32.3 pounds per square inch. All right, so back down here, I'm going to move this up a little bit. It says the car is safe to drive as long as the pressure is 12 pounds per square inch or greater. So what I need to figure out, right, this is when is equal to 12 pounds. So I'll say, well, 12 is equal to 35 E to the negative 0.008 T. This is the model I'm going to use to figure out how long until that car is unsafe to drive. So basically, I'm trying to solve this for time. So I'll divide both sides by 35, and again, a lot of the math involved here is very Algebra 2 is when you first learned how to do this. Now again, I've got my variable trapped up into an exponent, and my base is E, which indicates that I need to do the inverse, which which would be to natural log both sides. And basically it cancels it out, or I'm going to write it all out here for the first time we're doing it, but it's got a lot of pattern to it. Remember, exponents can come out front, property of natural logarithms, and the natural log of e is simply 1. So I end up with ln of 12/35 is equal to just negative 0.008 t. So to solve that for time, I divide by negative 0.008. And my time would be, and by the way, once you do a couple of these, you're going to get kind of in the rhythm of it. And there is definitely a pattern to them, a very similar way of solving every single one of them. I believe when you finish that off, you're going to get 133.805. You might want to go try that on your calculator, but minutes, because this is a time unit. All right, so I'm going to go to the next one here. How much time do I have? I'm at 10 minutes. So now I've got bacteria in the lab, and it says that the instantaneous rate of change, which would be dB, I'm going to use B for bacteria, over time, rate of change of the bacteria is directly proportional, K, to the number of bacteria present, B. That's my differential equation. All right? Now it says to solve it. Again, I could go through my separation of variables and I could integrate, etc. But what's going to happen is I'm always going to get that the bacteria is equal to the amount I started with, E to the KT. So what I really want to do then in a problem like this, kind of keep in mind, is they have to give you enough information so that you can, they have to tell you what it started at. If it's changing over time, I obviously, in order to predict the future, I need to know how many were there at the start. That's what I mean by B sub 0. They also must give me enough information to solve for K. And usually you get this one first, and it's given to you. They'll tell you, like, at time 0, the temperature is 42 degrees, or at time, in 2010, there were 4,000 people, where this survey starts in 2010 or something. So this will be very evident from the problem, the B sub 0. The K requires some solving. All right, so let's go take a look. Right away here it says, initially there were 5 billion bacteria. Well, that's my amount of bacteria at time 0. All right, so let's go set this up. Where am I? Write a particular equation that expresses the number of millions of bacteria as a function of hours. So here's my particular solution. I've got B is equal to the amount I started with, E to the KT. That's my model. I also know that I started at 5 million. So I'm just going to go put that in. If I put in a 0 for T, I get a 1, I get 5 when I plug that in. So there's that setup. Now, they also gave me that 3 hours later, it grew to 7 million. So what that means is 3, 7 is a solution. So I'm going to say that at time 3, 7 comes out. So the bacteria is 7 million, started at 5, E to the K times 3. Sorry, got a 3. I'm going to write that as 3K2 just to make it look a little nicer. So this is what I've got. All right. And what does it say? Write the particular equation and express the number of millions of bacteria as a function of hours. So what I really need to do now is go figure out what K is. Well, just like on the last one, I divide. I take the natural log of both sides, which is going to undo the E. It's just going to leave me with 3K. And note, I kind of have that similar pattern here where I end up doing the natural log of 7/5 divided by 3 is my K. And if you go do that on your calculator, I'm not quite sure what you get with that one. Let me take a look here. It looks like you get 0.112 for your K for that one. All right, so then it says to sketch the graph. Well, you've been doing that for quite a while with the graphing, so, exponential growth model you should be pretty comfortable with. But at 0, it starts off at 5 billion. After 3 years, it's up to 7 billion, and then you could go up to 10 and plug that into your model, and it's going to go like this. Okay? Now, I want to finish up my model over here, so I'm going to go back to my original right here. My bacteria model is going to be, my bacteria after time t is the 5 million I started with, E to the K times time. So if I want to predict what's going to happen after 10 hours, I just put it in for the time. So let's go down here and see what it's asking me